NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Voyager 1 was launched all the way back in 1977 and is now about 15.5 billion miles away from Earth, constantly moving at around 11 kilometers per second. Since it's so far away and it's such an outdated spaceship, many are wondering how we can still contact Voyager 1 after all these years. Where is Voyager 1 now? And how can we communicate with it?
NASA says that Voyager 1 has become the first man-made object to reach interstellar space, the cold, dark region between stars, far from the influence of our sun.
How we can contact Voyager 1. Even if Voyager 1 was sent out of Earth decades ago, we can still contact it. This is thanks to the remarkable design and coordination of NASA's Deep Space Network, a global system of radio antennas built specifically for communicating with spacecraft in the far reaches of space. Though Voyager 1 is now well beyond the edge of our solar system and more than 25 billion kilometers from Earth, the DSN makes contact possible by maintaining those ever-weakening signals and directing commands across unimaginable distances. The DSN consists of 3 primary ground complexes strategically placed around the globe, one in California, another in Madrid, Spain, and a third in Canberra, Australia. These sites are spaced so that as Earth rotates, at least one of them has a line of sight to Voyager 1, allowing for continuous communication. At each complex, there are extremely large dish antennas, some up to 230 feet in diameter, because when Voyager 1's transmissions arrive, they are so faint that only a very large and sensitive receiver dish can detect them. Voyager 1 itself transmits with a very low-power transmitter, which is even worse when you look at how far away it is from Earth. When its radio wave reaches Earth, the signal has faded to less than a trillionth of a watt, and it is an incredibly faint whisper from the edge of human launch capability. To make sense of these signals, the DSN uses highly specialized signal processing technology. Its systems filter out vast amounts of terrestrial and cosmic radio noise, amplify the faint signal, and then correct for Doppler shifts and other distortions caused by the spacecraft's motion, and then it reconstructs usable data and commands. Since Voyager 1 is so far away from us, the time it takes for a signal to travel one way is enormous. By the time we send a command, it takes about 21 to 23 hours to reach the spacecraft, and a similar time for the reply to arrive on Earth. That means every interaction is a multi-day cycle of waiting and trusting the technology. Meanwhile, NASA must carefully manage Voyager's limited power supply. Voyager doesn't use solar panels, as the sun's rays are far too weak, so its energy comes from radioisotope thermoelectric generators that slowly produce less power over time. As systems gradually fail or are switched off to conserve energy, NASA engineers are focused on which instruments remain active and when to turn off others, just to keep the communication link alive for as long as possible. For almost 5 decades, Voyager 1 has been in space, moving farther and farther away from our planet. It was launched in 1977 with a particular mission. Voyager 1 launch and mission. Launched on September 5, 1977, from Cape Canaveral on a Titan II IE Centaur rocket. Voyager was part of the ambitious Voyager program created by NASA. Despite being marked as number 1, its twin, Voyager 2, had launched a few weeks earlier on August 20. The aim was to explore the outer planets of our solar system by taking advantage of a once-in-a-lifetime planetary alignment that made a grand tour possible with minimal fuel use. Voyager 1's primary mission focused on flybys of Jupiter and Saturn. On March 5, 1979, it made its closest approach to Jupiter, giving humanity its first up-close look at its moons, rings, and magnetic environment. Then on November 12, 1980, it reached Saturn and offered detailed information about Saturn's rings and moons, including significant findings about Titan's thick atmosphere. Although it launched after Voyager 2, Voyager 1 actually overtook its twin because it followed a faster trajectory and had the benefit of the gravity assist flyby earlier. With its planetary tasks complete, Voyager 1 continued outward on an escape trajectory from the Sun's gravitational dominance. In August 2021, it crossed the heliopause, which is the boundary where solar influence gives way to the interstellar medium, thus becoming the first human-made object to enter interstellar space. A striking feature of Voyager 1 is the so-called golden record it carries. This is a gold-plated phonograph disc containing sounds, images, and greetings from Earth, designed as a time capsule or a message to any potential extraterrestrial finders. The mission's original design life was only about 5 years and was intended primarily for the Jupiter-Saturn visits. Yet, Voyager 1 has far exceeded expectations and continues to send back data for decades. From a scientific standpoint, Voyager 1 changed our understanding of the outer solar system. It discovered active volcanoes on Jupiter's moon Io, found faint rings around Jupiter and Saturn, mapped magnetic fields and charged particles, and revealed Titan's thick atmosphere. Now that it's in its extended mission phase, it continues to measure conditions in the interstellar medium, which is the space between stars, providing unique data that cannot be found by other aircraft. Voyager 1 is now in interstellar space and has become the farthest human-made object from Earth. Where Voyager 1 is now as of 2025, Voyager 1 holds the record for being the farthest flung human-made object in space, hurtling outward in interstellar space at about 169 astronomical units from Earth. That's more than 25 billion kilometers away. Voyager 1 left the region dominated by the Sun's solar wind, the heliosphere, in 2012, and it became the first spacecraft to enter what we call the interstellar medium. Although, depending on definitions, the boundary is a bit fuzzy. It is now journeying through a realm where the Sun's influence is minimal, and the galactic environment starts to dominate. Recent trackers put it in the constellation of Ophiuchus at a distance of about 25.3 billion kilometers from Earth, with light taking about 23 hours and 30 minutes to travel between us and the spacecraft. Despite being launched in 1977 and designed for a mere 5-year mission, Voyager 1 continues to send back valuable data. After a technical hiccup in November 2024, where readable science and engineering telemetry temporarily ceased, NASA engineers managed to recover full science operations by mid-2024. Some of the scientific instruments that are still operating are those measuring magnetic fields, plasma waves, and charged particles, giving us unprecedented insight into the region beyond the Sun's domain. In May 2025, NASA announced the successful revival of Voyager's backup roll thrusters, previously considered inoperable since 2004. This clever fix helps keep Voyager pointed toward Earth so that its weak transmissions continue to reach us. Recently, Voyager 1 returned data about the interstellar medium, which is the space between stars, and collected information on magnetic fields, plasma waves, and charged particles. It mostly collects non-imaging scientific data since the cameras were turned off back in 1990 to conserve power. The information that's being sent back now is helping scientists understand the heliosphere structure, the boundary where the Sun's influence ends and true interstellar space begins. Recent findings have revealed a wall of fire, of energetic particles at the solar system's edge, and some surprising similarities between magnetic fields inside and outside this boundary. But Voyager 2 has been running for almost 5 decades, and so it's already declining in its function. To stretch the mission for as long as possible, NASA engineers are systematically shutting down all the non-essential systems. According to NASA, the scientific data might wane by around 2026, but engineering data, like the spacecraft's status signals, could continue into the early 2030s, probably until about 2036. Engineering updates reveal that even as instrumentation winds down, the mission team remains actively engaged. Diagnostics, attitude control, and communication maintenance continue to hold pace. The successful thruster revival and software workarounds for memory faults illustrate how the mission remains alive through ingenuity and remote patches. But Voyager 1's location, beyond the heliosphere, means that it's sampling an environment that no other spacecraft has. It has made a lot of achievements ever since it was released, especially sending never-seen-before photos back to Earth. Achievements of Voyager 1 during its flyby of Jupiter on March 5, 1979. Voyager 1 sent back nearly 19,000 images of the planet and its moons. This was when we realized that Jupiter's atmosphere was far more complex and turbulent than we actually thought, with storms, fast winds, and dynamic cloud bands. Perhaps most spectacularly, Voyager 1 discovered active volcanoes on Jupiter's moon Io, the first ever volcanic activity observed on a planet other than Earth. It also discovered that Jupiter possesses a faint ring system, making Jupiter the fourth ringed planet after Saturn. In its subsequent encounter with Saturn, the closest approach, which happened on November 12, 1980, Voyager 1 provided stunning images of Saturn's rings, showing intricacies such as the braided nature of the F-ring, shepherd moons that shape ring edges, and an abundance of small moons previously unknown. The flyby of Saturn's largest moon, Titan, revealed a thick, nitrogen-rich atmosphere, and this caused scientists to consider complex chemical processes at work. In February 1990, the spacecraft turned its camera back toward the inner solar system and captured the iconic pale blue dot image of Earth from about 3.7 billion miles away. It was a humbling reminder of our place in the cosmos. Beyond that, Voyager 1 became the first human-made object to cross the heliosphere's outer boundary, the heliopause, in August 2012. It entered interstellar space by that time. Once it was beyond the sun's dominant influence, it started providing the first direct measurements of the interstellar medium, like magnetic fields, cosmic rays, charged particles, and plasma waves in this previously unexplained region. The achievements of Voyager 1 go beyond individual discoveries. Its data reshaped our understanding of planetary rings, magnetospheres, moon geology, atmospheric chemistry, and the boundary between our solar bubble and the galaxy. The mission also proved the value of gravity assists and long-duration operation, paving the way for future spacecraft such as Cassini, Juno, and New Horizons to explore deeper and further. Voyager 1's journey reminds us that even after all the years, with care, ingenuity, and persistence, it became a 50-year odyssey of discovery. It has expanded our view of what's in space, like volcanoes, distant moons, and interstellar space. But its age is already showing, especially since Voyager 1 is seeing a reduction in its power supply. Power has reduced. The power story behind Voyager 1 is a fascinating example of endurance, and it illustrates how a spacecraft that was designed for a few short years has kept ticking nearly 5 decades later. When Voyager 1 launched in 1977, it was powered by 3 radioisotope thermoelectric generators, RTGs. Each of these units converted the heat from the decay of plutonium-238 into electricity. When they were launched, those RTG produced about 158 watts each, according to NASA. Over time, things change. The fuel is decaying. The thermocouples have become degraded, and other losses have contributed to the gradual drop in output. As of about 2023 and 2024, the total output of Voyager's RTG is reported at around 225 watts electric. That means it's delivered less than half of its original electrical output after nearly 50 years in space. One source noted that Voyager is now generating less than 47% of its initial power. Because of this dwindling supply, mission engineers have had to make tough choices. Non-essential systems, including heaters, cameras, and other instruments, have been shut off or placed in standby to conserve power and extend the life of the core science instruments that are still returning vulnerable data. NASA also reports that each RTG loses about 4 watts per year of electrical power, so it's only a matter of time before Voyager 1 permanently stops working. Why does this matter? Because at such great distances, as Voyager 1 is in interstellar space, the spacecraft no longer depends on solar panels, as the sun's light is far too faint. It must depend mostly on this decaying nuclear power supply, not just for science instruments, but also for keeping its antenna pointed at Earth, managing its orientation, heating key systems, and transmitting faint signals back across billions of kilometers. To keep Voyager 1 functioning with limited power, NASA has adopted new strategies. For instance, they changed how voltage regulation backup circuits are used, so more of the dwindling power is allocated directly to science instruments instead of reserved safety margins. Engineers have also prioritized which instruments remain active, focusing on those measuring magnetic fields, charged particles, and plasma waves. All of this is data that only this mission can gather at the frontier of interstellar space. What does all this mean for Voyager's future? While the power output will continue to drop, the mission team expects to keep at least one science instrument operating into the 2030s, provided key systems remain functional. Eventually, when the power dips too low to maintain communications or orientation control, Voyager 1 will fall silent, but even then, it will still drift on its trajectory out into the galaxy. Who knows where it would later end up? Technical issues. Although Voyager 1's journey through interstellar space has been extraordinary, there have also been some technical challenges. One of these was an onboard computer memory failure that started in November 2023. In mid-November 2023, Voyager 1 began sending radio signals that were technically present as the carrier was there. Yet the data content was essentially gibberish, with neither engineering telemetry nor science data in a usable format. Investigation revealed that a portion of one of the spacecraft's 3 computers, the Flight Data Subsystem, which packages science and engineering data for transmission, had corrupted memory. About 3% of its memory had become unusable. As you can imagine, the faulty hardware couldn't be physically repaired since Voyager 1 is billions of miles away from Earth. So engineers devised a code workaround that relocated critical functions to other memory banks. By April, the spacecraft started transmitting usable engineering health data again. Another problem that NASA scientists faced was when the thruster valve was clogging, and there was an orientation control risk. Voyager 1 must maintain very precise orientation toward Earth so that its high-gain antenna remains pointed for communication. Its roll control thrusters, which were used to keep antenna alignment, have been suffering from propellant residue buildup and potential valve clogging. In early 2025, engineers successfully reactivated a thruster that had been considered unusable since 2004, restoring a backup orientation system and thereby extending the potential lifetime of the mission. If the attitude control failed completely, the antenna would drift, communications would be blocked, and the mission would end prematurely. Then in October 2024, there was a problem with an antenna pointing drift and transmitter mode changes. The fault protection system on board Voyager 1 was triggered after a heater command led to elevated current draw. This caused the primary X-band transmitter to be shut off automatically, and the spacecraft switched to the much weaker S-band transmitter, which was unused since 1981, as a fallback. The weaker S-band signal required longer integration and was less reliable, but it kept basic communications alive while engineers investigated the root cause and worked toward restoring the nominal X-band system. Another problem that Voyager 1 faced was having single-string aging systems with no redundancy. Many of the spacecraft's originally redundant systems have had one or more redundant lines shut down or exhausted. Components built in the 1970s are now operating far beyond their design life, and many failover paths are no longer available. For instance, the memory failure in the FDS meant that there is no longer full backup capability for that subsystem. This means any new fault might be irrecoverable and trigger the end of the mission earlier than planned. Voyager 1 also faced power and resource constraints that affected troubleshooting. Because Voyager 1's power budget is slowly shrinking due to decay of its radioisotope thermoelectric generators, mission engineers must also make trade-offs, like power, available for heaters, communications, instruments, and fault protection systems is decreasing. Combine this with the long signal delays and extremely long turnaround times for sending signals. Each troubleshooting step is high stakes and slow. Future Outlook Voyager 1 is powered by radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity. Over time, the power output is falling, as about 4 watts per year are being lost. Because of this dwindling energy, mission engineers are systematically shutting down non-essential systems and science instruments so that the most critical ones can keep running. For example, 2 science instruments were turned off in March 2025 as part of a power conservation plan. With careful management, NASA expects Voyager 1 to continue operating with at least 1 science instrument into the 2030s. Beyond that time frame, while the science instruments may be dead, the spacecraft might still transmit engineering and health data or remain as a silent ambassador floating through interstellar space. According to NASA, they might keep on communicating with Voyager 1 until 2036, since the spacecraft will remain in the range of the Deep Space Network. At that point, power or hardware failures will end all contact. But there's one milestone to watch. By November 2026, Voyager 1 is projected to be about 1 full light day away from Earth, meaning a one-way signal will take about 24 hours, and a round-trip signal about 48 hours. As that distance grows, communications will become slower and weaker, demanding ever more precision in command and data retrieval. Even once it stops sending usable data, Voyager 1's journey doesn't end. It continues to drift outward, escaping the sun's gravitational pull and heading into deeper parts of interstellar space. Years, centuries from now, it may pass through the outermost regions of the solar system, for instance, the hypothetical Oort cloud, or continue forever as a human-made object adrift in the galaxy. So, we remain in contact with Voyager 1 despite all the years that it has remained on Earth. Now, it's billions of miles away and takes up to 24 hours just to send a signal. What do you think is the most impressive aspect of Voyager 1's journey? Let's know your thoughts in the comments. So, thanks for watching this video, and we will see you in the next one.